Welcome back to Honors Calculus. In this video, we're going to be talking about absolute value. You should be familiar with the idea of absolute value already. The absolute value of a number ignores whether it was positive or negative and gives the positive value anyway, which is, once again, kind of a hand-wavy way of talking about a operation on numbers. So let's see if we can establish this one a little bit more concretely as well. My experience in algebra courses, the courses you've probably taken up until this point, you've probably mentioned absolute values several times and never really paid close attention to it or never really spent a lot of time in actually analyzing the absolute value. So let's take a look at the formal definition. Absolute value is defined using this three-piece equation, right? Conditional equation. If A is a positive number, then the absolute value of A is A. If A is a negative number, that means that the opposite of A is a positive number, and the absolute value of A is the opposite of A. And if A is 0, then the absolute value of A is 0. The first thing we have to do is make sure that we accept that this is a well-defined operation. And it is, or I wouldn't be saying this, but why? Remember back when we defined the positive numbers, we said that for every real number, exactly one of three things had to happen. That number was positive, the opposite of that number was positive, or that number is 0. So every real number must satisfy exactly one of these three conditions, never multiple, never none. This is a well-defined operation. It's a little bit chunky as it's written, so generally, we kind of simplify a little bit with a theorem that says that the absolute value of A is instead just two pieces, A, if A is greater than or equal to 0, and the opposite of A, if A is less than 0. And by taking things down and just having these two possibilities, it makes doing work with absolute value a lot easier. And you can verify pretty quickly without having to write out the whole theorem. If A is positive, A is greater than or equal to 0, absolute value is A, absolute value is A. If opposite of A is positive, that means that A is less than 0. Absolute value is opposite of A, absolute value is opposite of A. If A is 0, then A is greater than or equal to 0, and A is equal to 0, so the absolute value of A is 0 in either case. So in all three cases of the original function, this simplified version also works. So with that simplified version as our tool of choice, let's go ahead and start looking at a couple of other results. Again, some things that you have seen before. First one, for any real numbers A and B, the absolute value of A times B is the absolute value of A times the absolute value of B. And when we prove things involving absolute value, generally speaking, our goal is going to be to divide into several cases. The easiest case is if A is greater than or equal to 0 and B is greater than or equal to 0. Properties of inequalities says that A times B will also be greater than or equal to 0 in that case, which means that the absolute value of A times B is A times B, and that the absolute value of A times the absolute value of B is also A times B. By the transitive property of equality, these are the same thing. The second case I want to look at is where A and B are both negative. Once again, using properties of inequalities, if A and B are both negative, well then A times B is actually positive, which means that the absolute value of A times B is just A times B. But the absolute value of A times the absolute value of B is going to be the opposite of A times the opposite of B. But luckily, we can use the commutative and associative properties to multiply opposite times opposite. Negative and negative is positive. So this is really just A times B. And once again, absolute value of A times B is equal to absolute value of A times absolute value of B by the transitive property of equations. The third case is where things start getting a little bit trickier. In the third case, we have to look at A is greater than 0, not greater than or equal to. A is strictly greater than 0, and B is less than 0. Which means that A times B is going to be less than 0 as well. So the absolute value of A times B is going to be the opposite of A times B. And the absolute value of A times the absolute value of B is A times the opposite of B. But using the commutative and associative properties, that's the same thing as the opposite of A times B. So once again, transitive property of equality, absolute value of A times B is the same thing as absolute value of A times absolute value of B. All right, so I said in case 3, I had to look at A strictly greater than 0 instead of greater than or equal to, because the equals version is a little bit trickier. But actually really easy. It's just that the logic is slightly different. Right? If A is 0, then A times B is 0. The absolute value of A is 0, so the absolute value of A times absolute value of B is 0. Everything is 0, so everything's equal to each other, and that's case 4. And then the laziness kicks in. We can use a similar argument for A less than 0 and B greater than or equal to 0. Literally just take cases 3 and 4 and swap the letters A and B and rewrite them, and you're done. And the key here is that this exhausts all cases. We have looked at every possible combination of A and B, positive, negative, and zero in these cases, and the hand-waving argument of, yeah, we can just keep repeating this, but I'm lazy and I don't want to write it down. And because we've proved that this works in every possible case, we can just say that this works without having to think about it any further. A corollary to that theorem. I don't think I've used a corollary previously in this course. A corollary is a theorem which is really easy to prove based on the result of a previous theorem. Very often a corollary is essentially just restating the theorem. In this case, it's a little bit more involved than that, but it's just one more property of absolute value equal to each other. And the proof of a corollary is always very straightforward. In this case, the absolute value of b minus a is the same thing as the absolute value of the opposite of a minus b, right? Because b minus a is the opposite of a minus b. And then I can split that up using the theorem we just proved, and the absolute value of -1 is 1, and 1 times anything is that thing. So again, proof of corollary, always very straightforward. The next thing that I want to prove is the triangle inequality, which is another theorem. With such an evocative name, I want to talk about what the name means before I get into the heart of the actual proof. If you think about any arbitrary triangle and we name the 3 sides of the triangle, it must always be the case that the long way, a plus b, is longer than the direct path, c. Right? If I want to get from, can't quite reach over there, my green screen doesn't quite work. If I want to get from this corner to that corner, I can take the long path or I can take the short path. And the long path has to be longer. Otherwise, the thing you have is not a triangle. Right? Imagine a triangle where C is very long and A and B are both very short. Because A and B are both very short, you don't get far enough to connect at the other side. That's a very obvious thing. And when you study triangles in trigonometry, that's something that is very important. But it's also going to be the case in absolute value, which is a little bit hard to see the analog, which is why I wanted to talk about what this means in triangles first. Right? If you think about the long path to get there and you think about the direct path to get there, I think this will make a little bit more sense. So in terms of real numbers and absolute values, the triangle inequality says that for any 2 numbers, a and b, in the real numbers, the absolute value of a plus b must be less than or equal to the absolute value of a plus the absolute value of b. Right? If you have studied vectors previously, this addition makes sense. If you find the vectors added together, that's taking the direct path and then find the magnitude of that. Or if you find the length of each of the paths individually, that's going on the circuitous route. That's C and then A plus B in my picture of the triangle earlier. And just like our other proof on absolute value, I'm going to prove this by breaking it into parts. The proof is going to be a little bit trickier because I have an inequality and not an equal sign. And that's really the reason I want to show you this proof, so that you can see how proofs involving inequalities can work. Right? But if A is greater than or equal to 0 and B is greater than or equal to 0, then that means that A plus B is greater than or equal to 0. So the absolute value of A plus B is equal to A plus B, and the absolute value of A plus the absolute value of B is equal to A plus B. So that gives us the conclusion that absolute value of A plus B is equal to absolute value of A plus absolute value of B. And if they are equal, then it is also true that the less than or equal relation is valid. Right? If x is if x is equal to 7, then it's also true that x is less than or equal to 7. In general, that's less useful, so we never take that step, but it's absolutely true. And in this particular case, it is useful. The second case looks much the same. If A is less than 0 and B is less than 0, then that means that A plus B will also be less than 0. So the absolute value of A plus B is the opposite of A plus B, which is the opposite of A plus the opposite of B using the distributive property. And the absolute value of A plus the absolute value of B is the opposite of A plus the opposite of B. And once again, these two things are equal to each other, which means that they must be less than or equal to each other as well. In case 3, here I'm going to have A as greater than or equal to 0 and B as less than 0. In the previous proof, we had to separate the greater than case and the equals case instead of looking at them all at once. Here, once again, we're going to have to separate things. But it turns out that the separation that we need is slightly different. So let's look at the situation where the absolute value of A is greater than or equal to the absolute value of B. If that is the case, then A plus B will be greater than or equal to 0, which means that the absolute value of A plus B is equal to A plus B. Now, here's where things get weird. Because B is a negative number, I know that A plus B is less than A by itself. right? Since b is negative, a plus b is smaller than just a. Once again, a really weird step, but it should make a lot of sense now that you've seen it. And a is the same thing as the absolute value of a. And now, no matter what b is, if I take the absolute value of a and I add the absolute value of b to it, because the absolute value of b is positive, I'm going to get something bigger than just the absolute value of a. So I get, in this case, the absolute value of a plus b is less than the absolute value of a plus the absolute value of b. And if it's strictly less than, then it's also true that it's less than or equal to. Once again, as with what we did before, it's less useful that way, but it's still absolutely true, and that's what we care about. My next case, I'm once again going to have a positive, b negative. This time, the absolute value of a is less than the absolute value of b. So a plus b will be negative in this case, which means that the absolute value of a plus b is equal to the opposite of a plus b, which is the opposite of a plus the opposite of b. All right, I'm going to approach this slightly differently than I did before, because it's not immediately obvious that the opposite of b is positive, but it will be immediately obvious if I take absolute values here, right? Because a is positive, a is the absolute value of a. Because b is negative, the opposite of b is the absolute value of b. And I think you will agree at this point that the negative of the absolute value of a added to b is going to give you a much smaller thing than if you took absolute value of a and left it by itself and added b. Will usually give you a smaller thing, but it is actually possible that a is just 0. And if a is just 0, then we didn't change anything at all. So here, finally, I get the conclusion I want without having to do any extra steps. A plus b is less than or equal to absolute value of a plus absolute value of b. And once again, I'm going to say that a similar argument holds for a less than 0 and b greater than or equal to 0. Literally just swap the letters a and b in cases 3 and 4, and you have done it. And that will exhaust all possible cases, so the triangle inequality works everywhere. Yay. All right. That's a lot of theory of absolute value. Those properties are going to come back and be useful several times throughout the remainder of the course, although not directly useful for what I'm going to be doing for the rest of this video. Instead, I want to look at inequalities that involve absolute value. Once again, you may remember from a previous algebra class that absolute value inequalities come in a couple of different flavors. There is the convergent case and the divergent case, and you may have learned how to recognize them, how to deal with each one on their own. One thing that I can give you that will make your life a little bit easier is that we are only going to deal with the convergent case in this course. Those are the only absolute values inequalities that come up, so we can make the review here a little bit easier. And so my theorem here says that the inequality absolute value of x is less than c for some c greater than or equal to 0 is equivalent to the three-piece inequality opposite of c is less than x is less than c. And if we decide to change that for less than or equal, we just change less than or equal in these places and everything still works. And the proof there is actually pretty straightforward. If x, I'm sorry, if for any x, it must either be the case that x is greater than or equal to 0 or that x is less than 0. If x is greater than or equal to 0, then the absolute value of x is equal to x. And substituting that into the inequality gives us that x is less than c. If x is less than 0, then the absolute value of x is equal to the opposite of x. And substituting that into the inequality gives us that the opposite of x is less than c, which we can rearrange and get that that means that the opposite of c is less than x. And now we have two inequalities which are oriented in exactly the right way to give us a three-piece inequality. So for example, if I want to find the solution set for the inequality, absolute value of 2x plus 5 is strictly less than 9. Using my theorem, I have absolute value of thing less than some value, which means that the negative of that value is less than the stuff inside the absolute value is less than the thing by itself, 9. This is a fairly straightforward inequality to solve. Subtract 5 on both sides, or on all three sides of the inequality. Divide all three sides of the inequality by 2, and then write the result as a solution set in interval notation. Here's a similar problem for you to take a look at. the absolute value of 3x plus 1 is strictly less than 7. Solve the inequality and write the solution set in interval notation, very similar to the one that I just finished. Take a few minutes, see what you can do with that problem, and I'll see you in the next video.